Okay, welcome once again to the Maths Jedi channel. This is the next video in my A-level series, and this particular video focusing on binomial distributions. So I'm hoping you're tuning in and watching this. This links very well with the previous video on discrete random variables. So if you haven't seen that one, I would encourage you to check it out. And if you're new to the channel, please do leave a like and subscribe because that will help me out a ton. Now, binomial distribution is definitely an A-level topic, something you haven't seen before at GCSE, quite unrelated to a lot of things that you've seen at GCSE, but some concepts that will overlap. So there'll be some things that I will talk about that perhaps are familiar to you from before. First of all, let's talk a little bit about statistical distributions. Statistical distributions can be used to model different various concepts and outcomes. It tends to be that we model real-life examples with statistical distributions, and binomial is one such distribution. There are particular conditions under which the binomial distribution can be used, and you do have to learn those. So the first thing I'm going to talk about really is when a binomial distribution is relevant. So before I get started with that, let's just focus in on a couple of examples of binomial distribution. Here's an example that you might see here. This screen is featuring sort of one of those ball dropping things. And what we're going to do is we're going to fix the chance of the ball going right as 0.5. So the ball can go right 0.5 at a time and can go left 0.5 at a time. We're going to release 100 balls and we're going to see what happens. This is 100 balls being released, and you can see as they're falling down, half are going to the right, half are going to the left. And it should be that if you've dropped enough balls, it should really sort of even it out. So hopefully after 100 have been dropped, you can hopefully see sort of 50% going to the left and 50% going to the right. So roughly half hopefully should go to the right and roughly half go to the left. Of course, there's an odd number of holes here, which makes it slightly more tricky. But roughly you can see the distribution, how it works. You can see the end points are completely zeroed out, but there is a sort of mirroring going on with these numbers. So 10 is roughly the same as 12 and 4 is roughly like 2, and you can see the mirroring as we go through. So that's a good example where a binomial distribution could be used, because either it goes to the right or it doesn't. And this symmetrical nature is something which we use to our advantage a bit later on. Here's another slide that talks about binomial distribution. This is talking about a spinner. Spinner divided into 4 equal size sections. So you can see it here, and they're marked 1, 2, 3, and 4. And it says if the spinner is spun 6 times, how likely is it to land on 1 on 4 occasions? Well, they've used a bit of notation here. They said one possible sequence could be 1, 1, 1. So you get all the ones in a row, and then not 1, and then not 1. So let's just see how we work that out. Let's see what happens first if I spin the spinner. So here am I spinning the spinner. Oh, and I do get 1. That's good. If I spin it again, what do I get this time? I get a 3. And what do I do if I get it again? I get a 2, and again, I get a 3. And of course, you could go like that for a long, long time, but we're looking at one possible sequence here that I could have got 4 ones in a row and then not 1 and not 1. What are the chances of that happening? Well, first of all, we talk about this notation here. The amount of variance that you've got in 6 different throws are what we call 6 factorial. Now, 6 factorial is a new concept you haven't seen before. A factorial means you multiply numbers up before it. So 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. And that's because we're spinning the spinner 6 times. You have 6 factorial ways of that happening. 6 times 5 times 4 times 3 times 2 times 1. On the bottom, we only want to look at 4 possibilities. The 4 possibilities of you getting 1. So what's the chances of you getting 1? Well, you have 4 times that happen, so 1, 1, 1, 1. So there's 4 factorial ways of that happening. 4 times 3 times 2 times 1. And then you've got 2 factorial ways of it not happening. So you have to take that into account at all, because you want these 2 to happen as well. So there's 2 different factorial ways of that happening, 2 factorial ways of that happening, 2 times 1. Now we shorten this notation up to 6 choose 4, and you should be able to find on your calculator button the choose button. I'll just highlight that for you for 1 minute just so you can see it. So on this calculator here, you can hopefully see, I'll just bring it up over here, the end choose button is right down here. It's above the division button. You can hopefully see it just above there. Okay, so if you've got one of these calculators, just have a look above the division button. You'll find the end choose 4 or the end choose R button. Back to the PowerPoint. and then we're going to just click that. So 6 choose 4 was what we were looking at. That's the number of ways in which you can have this sequence occur, because you could have had 1 followed by not 1, not 1, 1, 1, 1. You could have had not 1, not 1, 1, 1, 1, 1. This is the amount of ways of this sequence occurring. It's quite a number of ways if you work it out. It's arranging 6 items where 4 are of one kind and 2 are of a different kind. Now, also, we have to take into account the probability. We know that there are 1/4 of the chances of us getting a 1, and that's got to happen 4 times in a row. And we also know that to get not 1, 3/4 of the time, that has to happen twice. So we've got to look at the probability of getting 0.25 4 times in a row, and then 0.275 2 times in a row. But there are 6 choose 4 ways of that happening. So all these different ways of these two things occurring. So you've got to multiply by this 6 choose 4 figure and you get your 0.0330. Now what's going on here is a binomial probability being calculated. And so it's important to take into account what is happening with regards to the number of variants that you could get, the number of different sequences that you could get, the probability of it happening and the probability of it not happening. Okay, so that's what's happening in this particular calculation to get this 0.0330. And this is a very common calculation within binomial distributions. Now, as I mentioned earlier, the binomial distribution is only used when conditions are met, and these conditions do need to be memorized. There are 4 or 5 different conditions. They tend to be 4 in some and 5 in another textbook. It just depends on what textbook you read. But generally, these things are true. You will have to have a fixed number of times that something occurs. That's always true. There are also times when the trials are independent of one another. So you can't use binomial distributions when you're dealing with conditional probability. So that's worth mentioning. Each trial has 2 possible outcomes, sometimes referred to as success and failure. To be honest, I just say it has 2 outcomes. Sometimes that could be 6 and not 6. In the previous example, it was 1 and not 1. So every time you're having 2 possible outcomes. Lastly, the probability of success remains constant. That's the one that tends to be overlooked. So these 3 are commonly listed in textbooks. This last one tends to be a bit more optional, but it is true that the probability of a success has to stay constant. It can't vary. You would argue that these 2 are dependent upon each other. If the events are independent, then of course the success should be constant. Now, if the above conditions are satisfied and x is the random variable for the number of successes, then we refer to a binomial distribution, which we use a capital B to represent. And we say x is represented by a binomial distribution of n trials with the probability of success being p. So n trials, probability of success being p. We call those 2 things parameters. Now, let's have a look at these different situations and see if we can figure out what's going on with these, see if we think these are valid for binomial distributions. So this first one here is talking about a lady Joan who's taking a multiple choice examination consisting of 40 questions. X is the number of questions answered correctly if she chooses each answer completely at random. What do you think? Is this binomial or is this not binomial? Well, let's just tick off through the list and see if we can identify whether we think this is binomial or not. First of all, are there 2 outcomes? We would argue she either gets it right or she gets it wrong. So there probably are 2 outcomes. Is there a fixed number of trials? Well, yes, because we've got 40 questions. Are the events independent? Well, yes. Are the outcomes independent? Yes, the outcomes are independent because she's doing these things at random. So they don't have any influence on each other. Finally, are the chances of her getting it right fixed probability? You'd argue if it's a multiple choice examination and all the multiple choice examinations questions have 5 options, for example, and that stays as 5 options, then the probability should stay constant. So I would argue that this should be a binomial distribution. This second example, let's have a look at this. A bag contains 6 blue and 8 green counters. James randomly picks 5 counters from the bag without replacement. X is the number of blue counters picked out. What do you think? Is this binomial or is this not binomial? Well, let's go through the list again. It's true to say these are either going to have blue or not blue. So there are 2 outcomes. There are a fixed number of trials because he's got 5 counters. However, in this particular example, it's not independent because this is without replacement. So once you take a counter out of the bag, the other ones are affected by what you're taking out of the bag. So this has to be something that's not binomial. This last example is a bag containing 6 blue and 8 green counters. Jan randomly picks 5 counters from the bag, replacing each counter before picking the next. X is the number of blue counters picked out. So in this example, there are 2 outcomes, blue or not blue. There are a fixed number of trials. They are independent because she's putting them back in the bag, and the probability should remain the same. So this should be binomial. Let's look at these ones. John throws a dice repeatedly until he obtains a 6. X is the number of throws he needs before a 6 arises. Again, there are 2 outcomes, 6 or not 6. Are there a fixed number of outcomes? No, because the number of throws could vary, so this can't be binomial. Then again for number 2, Judy counts the number of silver cars that pass her along a busy stretch of road. X is the number of silver cars that pass in a minute. So just looking at this, you have 2 outcomes, silver or not silver. Do you have a fixed number of trials? Well, Judy's counting within 1 minute, and you could argue that the amount of trials would vary according to what minute she's picking. So actually, I would say the number of trials is not fixed, and for that reason, this can't be binomial. Lastly, Josh is a midwife. He delivers 10 babies, and X is the number of babies that are girls. Again, you have 2 outcomes, girls or not girls. There are a fixed number of trials. Is it independent? Does one arrival of a girl affect another arrival of a girl? You would say they are independent events. And so in this example, it is binomial. So for a binomial distribution in general, you're looking at a key formula here, something you have to remember for your exam. And this is also in the book and worth remembering what you're looking at here. The probability of an outcome occurring will always be the number of different ways in which that outcome can occur, the number of successes, the number of failures. In the previous example with the counter example, it was 6 choose 4, 0.25 to the power of 4, 0.75 to the power of 2. It's no surprise that Q and P both add to 1 because they're mutually exclusive events. Either one happens or the other happens. So that's why they should add to 1, and that's why this formula is always true. Remembering again, number of sequences, number of successes, number of failures. Here's an example. If you're looking at a binomial distribution with the number of trials 12 and the probability of success 0.4, we're being asked for a probability of X being equal to 3. Well, what are the chances of 3 being successful? If you're throwing whatever it is 12 times or doing the trials 12 times, is going to have this first number here will be 12 choose 3. 12 choose 3. It's the number of sequences that occur when you have 12 objects and you're choosing 3 of them. 12 factorial over 9 factorial, 3 factorial. This here is the probability of success, 0.4 occurring 3 times. And this is the probability of failure, 0.6 occurring 9 times. Note that these 2 numbers, these 2 indices, should always add to 12 because that's the number of trials I had. And you should expect these indices always to add to the number of trials you have. When you work out all these things on a calculator, you'll get 0.142. For more than one, you have to be very careful just to use the best judgment that you can. Because this is an infinite set, you have to be careful about how you're doing these particular calculations with inequalities. It's easier, for example, because they're mutually exclusive events, to look at the probability of 0 and the probability of 1, add those up and take them away from 1. So what's happening here is that's exactly what they're doing. They're working out the chances of getting 0 successes, getting 1 success, and then taking it away from 1. This is a chance of getting 0. This is a chance of getting 1. They add them up and take them away from 1. Just to refresh, 0 is a logical option to pursue. The chance of getting 0 successes always has to be examined. Here's another example. The probability that a baby is born a boy is 0.51. A midwife delivers 10 babies. Find the probability that exactly 4 are male, the probability that at least 8 are male. Well, first of all, let's take that into consideration. This does not telegraph that this is a binomial distribution question. So you've actually got to do a bit of thinking here to make sure you have got the right distribution with the right question. First of all, are there 2 different outcomes? Well, yes, because we've got boy or not boy. Are there a fixed number of trials? Yes, because there are 10 babies. Are the events independent? Well, the chance of one boy being born and the chance of another boy being born, they shouldn't affect each other. So they are independent. Is the probability fixed? Well, yes, because we're told in the question it stays as 0.51. So we know we're dealing with a binomial distribution question. The minute we know we're dealing with a binomial distribution question, our first step would be to establish that binomial distribution. How many trials are we doing? 10. What's the chance of success? 0.51. If we're looking at exactly 4 of them being male, we need to work out the chance of those different sequences occurring. This is 10 different trials. Choose 4 because there's 4 males. This is the chance of success, the chance of failure, and this is your outcome. To work out at least 8 are male, that's 8 or more. And again, hard to do that unless you're working out 8, 9 and 10, or you could have done 1 minus 7 or less. This is probably the quickest way. Here they are working out the probability of it being 8, the probability of it being 9, the probability of it being 10. Note how in 10 ways you've got 0.51 to the power 10. You don't have any other outcome. And that's because if you do it on the calculator, 10 choose 10 is 1. And 0.49 to the power of 0 is also 1. They add up all those different probabilities and they get an answer 0.0621. Some things to look for. Again, note how the indices add to the number of trials. Note again how the probability should be less than 1. Be careful that you've taken into consideration all the different outcomes that are possible. Okay, time for you to do some work now, but let's look at a couple of questions on your textbook. So I'm going to pull up your textbook here. We're going to have a look at page number 90. So on page number 90, there are 3 questions that I'd like to concentrate on. Question 6, question 7, and question 8. So this one, and this one. Now for each one, first of all, I'm going to go through the steps that you would do to check that you're doing a binomial distribution, because nowhere in these questions does it really say that apart from here, and this one doesn't say it at all, and this one doesn't say it at all. So let's just read this question together and understand what's going on. Well, firstly, the probability of a switch being faulty is 0.08. A random sample of 10 switches is taken from the production line. Let's look at this sentence again. Faulty or not faulty? Fixed outcomes. 10. Consistent number of trials. Independence. One switch being faulty doesn't affect another one. Probability being fixed, 0.08. So it must be a binomial distribution. And that's what part A is asking for. Define a suitable distribution to model the number of faulty switches in the sample and justify your choice. So basically you put that into words and you justify your choice. In this case, X will be variant or sampled by a binomial distribution with the number of samples, trials 10, and the probability of success 0.08. It's very strange that we view the success as the faulty things here, because you probably would say faulty isn't being successful. I understand that, but in this question we always do take the probability into consideration as 0.08, and we do say that is a success. Find the probability that the sample contains 4 faulty switches. So we're being asked for the probability of x being equal to 4. Well, let's scribble over here. If we're being asked for the probability of it being equal to 4, we need to take into consideration how many different ways that could occur. We have 10 different trials. So we're going to start with 10, choose 4. And then we're being told that the chance of success is 0.08. So we have to multiply that by 0.08 to the power of 4. And then we have to have the chance of failure, 0.92. They have to add to 1. And this will be to the power of 6. Again, spot the indices should always add to the number of trials that we have. Let's bring up the calculator. So just move it to one side slightly. Okay, so here's my calculator. I'm going to do 10, choose 4. So notice 10 choose 4 here. We're going to multiply it by 0.08 to the power of 4. And we're going to multiply that by 0.92 to the power of 6. Be careful how you note it all in. This gives me a number 5.215 times 10 to the minus 3. So in terms of my answer, it's 0.00522. Try and give it to 3 SFs unless the question states otherwise. And that's the answer to that particular question. Let's just check that. So 0.00522. And you can just get rid of annotations there. And you can see the answer here, 0.00522. So we're correct. Question 7, we're going to look at that now. So it says, a particular genetic marker is present in 4% of the population. State any assumptions that are required to model the number of people with this genetic marker in a sample of size n as a binomial distribution. So what assumptions are you making? You're assuming that people are either having the genetic marker or they don't have the genetic marker because you want two outcomes. You're assuming that probability of 4% stays fixed, doesn't change. And you're also assuming the genetic marker is independent of another person having a genetic marker. Those are quite a big assumptions that you'll have to make, but those must be the assumptions that you're trying to make here in order for this to be binomial. Check that through. And you can see there are only 2 outcomes for genetic marker. There is a fixed probability of people having the marker. We did miss this one, fixed sample size, but that was fairly obvious from the question itself because it does say sample of size n, but it is worth mentioning. Of course, the question's only worth 2 marks. I'd imagine that 2 of those would be enough to get the marks. Part B says, using this model, find the probability of exactly 6 people having this marker in a sample of size 50. So what distribution do we have here? Well, we have a binomial distribution again, 50 trials, but this time the chance of success is 0.04 because it's 4%. So this must be my binomial distribution. We want exactly 6, so we want the probability of exactly 6. How many different ways of that happening? 50, choose 6. Chance of success, 0.04 to the power of 6. And chance of failure, 0.96 to the power of 44. You need to work all this out on the calculator, which I will do now. Oops. So here's my calculator. Let's just reset that. So here we are. 50 choose 6 to start with. Multiply that by 0.04 to the power of 6. multiply that to the power of 0.96 to the power of 44. And you get 0.0108. Again, try to give it to 3 SFs unless you're stated otherwise. .0108. Let's double check that. Just need to turn the calculator off. Okay, and here we are, 0.0108. Great. One more to do. Question 8. A dice is biased, so the probability of it landing on a 6 is 0.3. Hannah rolls a dice 15 times. State any assumptions that are required to model number of 6s of binomial distribution and state distribution. Well, let's look at our checklist. 6 or not 6, 2 different outcomes. 15 times, so fixed number of trials. Are the events independent? We would argue yes, because the dice landing on 6 the first time doesn't affect whether the dice lands on the 6 the second time. And then you're hoping the probability remains fixed. So assumptions for a binomial are all there. Which binomial distribution is it? It's a binomial distribution of 15 trials. Chance of success is 0.3. Part B says find the probability that Hannah rolls exactly 4 6s. So we're being asked for this. What are the different sequences that we can use? How many different ways can that happen? 15, choose 4. I hope you're getting the hang of this. Number of successes, 0.3 to the 4. Number of failures, 0.7 to the 11. Again, checking that these two indices always add to that. We'll get the calculator up and we'll have a look at this. Put this into the calculator. Let's get rid of this, it's not in the way. Let's see what this makes of it. So 15, choose 4. Chance of success, 0.3 to power 4. Chance of failure, 0.7 to power of 11. 0.2186, so 0.219 to 3 significant figures. Again, 3 significant figures unless stated otherwise. Just take a look at the answer to make sure we're there. And 0.219, so that's fine. The last question says find the probability that it rolls 2 or fewer 6s. So that's something we're going to have to do carefully. So chance of 2 or few 6s will be 0, and the chance of getting 1, and the chance of getting 2, because it's 2 or fewer. Don't forget the 0, that's the one that everyone forgets. We need to work out the chance of getting 0. So what's the chance of getting 0? We have, well, 15 ways in which 15 total ways in which it can happen. 15 choose 0. If you do 15 choose 0 on your calculator, 15 choose 0, just try it. 15 choose 0 is 1. Okay, there's only one way of you getting no 6s at all. Okay, there's only one way of that happening. So that's important to mention. Okay, in the 15 throws, one way of you getting no 6s. Chance of success, well, you're only going to have 0.7 because there is no 6s, so you're going to get 0.7, but 15 times in a row. Chance of getting 1 would be 15 choose 1, and then chance of success 0.3 to power 1, and then 0.7 to the power of 14. Again, noting that these two powers should add to that one. Chance of getting 2, different ways in which that can happen. 15 choose 2. Chance of success 0.3 squared. Chance of failure 0.7 to the 13. These again should add to 15. Add all those up together, use a calculator to do that, and you should get 0.127 I did it earlier, so I know that's what it makes. So you just need to use the calculator really carefully. The tricky one is the 0. Just make sure you never forget the 0. Let's just double check our answer is correct. And it's down here, so I need to double check. So 0.127, let's just trash my annotations. 0.127 there, you can see it there. So have a go at those, make sure you've got that down. This exercise now is there for you to try and practice. Make sure you go through and practice the remainder of that exercise. So that's exercise 6B. I'd like you to go through and do that, please. I will put the answers onto the system for you to find. So please have a little look and go through with those. Make sure you're ready. And the next lesson, we're going to look at this next topic starting under here, the cumulative probabilities. That's what we'll look at next time when I'm back to see you again. In the meantime, I hope you have a good rest of the week, and I look forward to speaking to you again soon. Bye-bye.